Alright, let's begin 7.6. In this, we are going to turn our attention to inequalities. So 7.5, 7.6 are very much connected. At 7.5, we learn how to graph parabolas. And in this section, it's going to be somewhat like graphing. In fact, there's two approaches. There's the algebra approach to doing this. Then there's also the geometry approach, or the graphing approach to it. We'll do the algebra method, and I'll show you sort of the geometry behind it as well. So incorporate those two together. But it is thinking about the graphing process here. Also, see how I connect 7.5 to 7.6. All right, so here's what we got. We have a trinomial or a polynomial, quadratic, that is actually an inequality as opposed to equal signs. Equal signs, we've been doing this all this time. In fact, we've never had an inequality that had a we never had a quadratic expression connected with an inequality yet. So this is a little bit new stuff. So notice there's four different options, of course. There's the trinomial that's less than 0, trinomial that's less than or equal to 0, which means I do want the 0 as well as the stuff that's underneath the 0. I have a trinomial that's greater than 0, so I don't want the stuff that's what's hitting 0. I want it when it's above the 0, and then of course the trinomial when it's greater than or equal to 0. So I want the stuff above the 0. I also want it when it equals the 0. So there's our four options here. Let's go look at example number 1 first from the textbook itself to see how this works. Alright, just a few little changes I'm going to make to the textbook here. So solve x squared minus 2x minus 8 is less than or equal to 0. And the way the book does it, it starts solving in an inequality. And then what it does is it factors these two. And then it talks about the signs, and I don't want to do it that way because then you have to plug in the numbers into each of these and try to figure out each of these the way they work. And that's not the way we want to do it. We really want to be able to combine these together. So I'm going to do a little bit different than the textbook here. And I think it's a little more straightforward method here. But let's see, what should I want to do? One thing we should think about, and let me jump back to the previous problem here. Oh, you know what, let me just go to this first here. So this is taken from a different textbook, but I thought it explains quite a bit here. Technically, if we think of an x squared, we'd think of a parabola, like as we graphed in 7.4. So really what we're going to try to figure out is if it's compared to 0, we're going to say, okay, when is it below the x-axis or when is it above the x-axis? Really, that's the question when you start comparing things to 0. So this is a graph when it's going to be below or under the x-axis. And in this case, check out something. Oh no, this is from your textbook. Okay. Notice the solution set. The solution set is just the range. It's the x values that make that true. So the answer for this problem, when is this parabola going to be less than or equal to 0? It's going to be true from -2 to +4. It's really a connection between the last problem here. It's true in this area, but I want to. Sometimes we think of when is this parabola going to be above or equal to 0. So if you're thinking about that, here's your parabola. It goes underneath 0 here. So when you talk about being greater than 0, you're really talking about sort of these endpoints right here. You're saying, okay, the graph is above 0, and all the negative numbers up to negative. Let's just say this was a -1 here, right? And then anything above +1 will do. So there's kind of two characteristics. You're either meeting in the middle or you're going off two directions. If you think of this as inequalities, I think you think this is an AND statement, right? AND statement bunches up in the middle. The OR statements go off to the side. That's a little connection there. But anyways, let's go with number 1. Before we get there, let me just think about one interesting concept here. Let's say we have a parabola. Parabola is up here. So now, as the parabola comes down like this, Here's my question. Is there ever a time where a parabola coming down could become negative without going through 0? So when a parabola is coming down like this, the question really is, does it has to hit 0 in order to go underneath? And answer, yes. When a parabola goes like this, then comes back up like this maybe. So notice if it's positive here, it's above the x-axis, above the x-axis. Let me change that. Above the x-axis, it hits the 0 and then it goes underneath, below the x-axis, and then it hits the 0 again, it hits the x-intercepts or the x-axis, and then it finally is able to go positive. So real quick here, if you do have a sign change, meaning positive goes to negative or negative going to positive, so positive y values going to negative y values, it has to go through a 0. If you have negative y values and all of a sudden they change to positive values, you know that there's a 0 that it had to hit. So that's going to be real crucial for us. I think now we have the concepts ready to start number 1. So here's the way I do it. Here's the way most algebra textbooks do this. We're going to take this trinomial and we are going to make an equal out of it. And the reason why I'm doing this is I want to know where it hits the 0. That's my question. When does this hit the 0? Because I know if it's the 0, that's when the sign change is going to occur. That's when it goes above to transition to below the x-axis, or from below to above. Once I make an equal sign, hey, look at this. These are all the stuff I know already, even from chapter 1, how to factor stuff. So can you factor x squared plus 2x minus 15? And yes, that's going to be factors of 5 and negative 3. So x plus 5, x minus 3. Set each of them equal to 0. How about x equals negative 5, x equals positive 3? And here's what I got. I know that this graph hits the x-axis at negative 5, so we're going to put a big old dot there. We're going to put a big old dot at 3. And we're going to color in that dot. Alright, so some thinking caps here real quick here. I know where it hits the 0. So now the question is, I know it hits the 0, so therefore it changes from positive to negative, negative to positive. So now I'm going to use some test points. But notice what we did is we solved an equation. We solved an equality. But my original problem is an inequality. When is this graph going to be less than or equal to 0? That's my question. So here's what I'm going to do. I'm going to plug in a test point. So pick anything that's a little less than negative 5. It doesn't matter. Negative 6 would work. Negative 10 would work. Negative 100 would work. It's just as long as this number's less than negative 5. Now what I'm going to do, I'm going to pick negative 6. And I'm going to plug it back to my original equation just to find out if it's true or false. Again, we did this before when we were graphing lines. So when I do that, I give myself a 36 minus 12 minus 15, and then makes a 9. 9 is less than or equal to 0. Is that a true or false statement? That is a false statement. Okay, here's what I got. I put a little f on top of the negative 6. I know this is false, so I know at this graph is not underneath or less than or equal to 0 here at negative 6. I know also that it can't be less than or equal to 0 at negative 7 or negative 8 or negative 9 because it would have to cross through a 0 to make that happen. So then I can be assured if I go out all the way to negative 100, it's still going to be false statements. So really in a sense what we just figured out was we have false, 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 all the way until we get to negative 5. Now negative 5, there may be a change, there may not be a change, but this is false. So now let's pick a number between negative 5 and 3, and of course the easiest one we can is 0. Let's pick that 0. 0 plugs in into the original equation, and I get myself a negative 15 is less than or equal to 0. That is true. So from negative 5, it's true at 0, therefore I know it's going to be true at 1, and it's going to be true at 2, at negative 1, negative 2, negative 3, negative 4, negative 4.5, negative 4.99. So this whole entire region really is true. That is, this graph is below 0 during this time. If it has to go above 0, I know it has to hit a 0. So then let's pick a test point. bigger than 3. You can pick 4 if you like, you pick 5, you could pick 10, it doesn't matter. Plug in a 5 into that original equation, makes 25 plus 10 minus 15. Gets you 20 is less than or equal to 0. I don't think so. That is also false. Alright, now, real quick here, we got to think about this fact right here. Is, do we include the times that this graph actually hit 0? Do we include this point here? Do we include the -5 or not in our final answer? And that is all dependent upon this little bar line right here. We're saying when is this greater than or, I'm sorry, when is this less than or equal to 0? That little equal to part is saying I'm going to include the endpoint. So I'm going to put brackets. Brackets means we're including the endpoint. Parentheses means we don't. And the brackets always face towards the true side at +3. There it is. This is all the true stuff. Alright, so there's my graph of my answer. And the answer could be written in 2 different ways. Something called inequality notation. I think you know this already. And then something called interval notation. Let's do both here. Inequality notation. You're saying -5. The number that I want is -5 is less than or equal to the number that I want, and the number that I want is less than or equal to 3. There's my inequality notation of this graph. Alright, there's also something called interval notation. Interval notation follows very close with the graph here. It just says this, bracket -5, 3. So beginning endpoint and shows if I'm including it or not. Alright, so that's the algebra method real quick here. We find all the zeros. As soon as we find all the zeros, the only sign changes could occur is in between the zeros. We test each of the intervals in between the zeros. We find out which interval is true, and done. Alright, how about the graph? Well, you could have, if you did your homework for 7.5 and you really like the graphing section here, you could understand that, you know, since there's a positive in front of x squared, remember the concave up and concave down issues here that we talked about? Since this is a positive in front of x squared, we know it's concave down. And then we also just figured out our x-intercepts. That's cool. So then the graph sort of looks like this. Starts off high, goes down, goes down, hits the x-axis at -5, goes underneath the x-axis, hits the x-axis at +3, and then climbs back up. So this question is, when is this parabola less than or equal to 0? Or when is this parabola underneath or equal to the x-axis? It's right here, from -3 to 5. So if you feel very comfortable with graphs of these parabolas, you don't need to do the test points. You just need to figure out your x-intercepts, and then just know the shape of this graph. What's the shape of the graph? The shape of the graph would be this right here. Alright, number 2. What happens if we're not comparing it to 0? We're comparing this to 2. Alright, well, we don't like that. We do want to compare everything to 0. So this is what we're going to do. We're going to subtract 2 from both sides. And once we subtract 2 from both sides, it allows us the whole concept of comparing it to 0 anyways. So we're going to make it equal to. Subtract 2 from both sides. And we're going to factor. This one's a little more difficult for factoring. The only way to get a 2x squared is a 2x times x, and then you've got to figure out whether the 2 or the -1 is going to go, or the positive 1 or -2, whichever way the numbers work out. And I'll let you guys try it. Go ahead and see if you can factor that by yourself. Alright, and this is what I got here. I got a +2 at the end, -1 here, so therefore I get myself a 4x, subtract x to give me the 3x in the middle. Alright, factoring, solving each of those cases here gives me a +1/2 or -2. So again, these are my zeros. These are my x-intercepts. So at 1, 2, 3 there, -1, -2, -3. And there are my 2 dots here. So a half is halfway between 0 and 1, and negative 2. Alright, just like the previous problem here, let me go with test points. Pick negative 3 as my test point here. Plug it in. Test point. Negative 3. Plugging back into my original equation. And again, all I want to know is true or false. So that's 9 times 2 is 18. Minus 9 is greater than 2. Yep, that is true. So negative 3, it is true. Alright. If you can pick a 0, choose a 0. At this point, since the 0 is chosen, we're testing x equals 0. And the comparison is 0 greater than 2. I don't think so. That's a false statement. Alright, and picking a test point, x equals 1. Easiest one to pick, right here. 5 is greater than 2. I don't think so. That is a false statement. Oh, I'm sorry. 2 plus 3 is 5. 5 is greater than 2. Yeah, that is a true statement. Oh, and I didn't get to this part right here. Are we including the endpoints now? Are including when it's equal to 2? And with the greater than symbol, no, we're not. We just want to when is the graph above 2. Well, that means we're going to have to put it in a parenthesis, and we're going to shade towards the true side. Put it in a parenthesis, shade towards the true side. Okay, this is the other one here. This is when it goes off 2 directions here. How do we do this? Interval notation says negative infinity all the way up to negative 2 with a parenthesis. And we have to account for this little gap right here. We've accounted by a big O U for union, starting off with a parenthesis at 1/2 and then going off to infinity. Alright, interval notation. Inequality notation. X is less than negative 2 or x is greater than I'll fix that up real quickly here. Or x is greater than 1/2. There it is. Phew. Good, I caught that. Now, before we go on to the next one here, let's think about this is a graph here. Let me choose a different color here. How about, let's go with purple here. So remember, this is the parabola that we're thinking about right here. How does this graph look like? Well, you know it's a positive 2, so you know the graph is concave up. It comes down, so if I were to make a graph, it'll sort of look like this. Graph is coming down, crosses the x-intercept here. I'm not sure how it turns around, where it turns around. I'm not interested in that. I'm interested in what crosses the x-axis again and goes up. So now the question is, when is this graph technically greater than 0? Oh, it's greater than right here. It's greater than when it's always above the 0 here and above the 0 here. Therefore, there's the answer. So there's a connection to the graphing aspect of the parabola. Alright, now let's go on to number 3. Number 3 will work a little bit with number 3 here. Alright, so first things first, let's put a little equal sign on here. So x squared plus 10x plus 25 is equal to 0. We're going to find all our zeros real quickly here. And this one's a fun one to factor here. It's x plus 5x plus 5. Now, since you have the same exact factors, you don't need to solve both of them. What you do is you're going to solve one of them to a negative 5. And of course, 1, 2, 3, 4, 5. Put a dot there. So in this case, this only splits off into 2 different intervals. It's either less than negative 5 or greater than negative 5. There's only one change here. So let's go for it. Let's pick a test point, something less than negative 5, and negative 6 works out pretty good. So let's plug in negative 6 into the original inequality. And let's see what happens here. 36 minus 60 plus 25 gets you 1. Ooh, that was a close one. 1 is less than 0. Is that true? 1 is less than 0. That's false. That doesn't work. Alright, moving to the other side. So the right hand side of -5 now, and the easiest one to plug in is 0, of course. So back to the original equation, 0 gets plugged in, 0 squared plus 10 times 0, still 0, plus 25 makes 25 less than 0. That is a false statement. Hey, that's weird. It's false on this side as well. So now the question is, what's the answer? Now real quick, I guess we should do this here. Are we including the 0? Are we including when the graph is right at 0? So going back to our problem here, no, I'm including when this parabola is less than 0. So answer is going to be no solution. There it is. There's never a time where this graph goes below 0. So let's look at the graphic implications over here. So by getting this -5, and we'll have one x-intercept. Well, we figured out it starts off high, comes low, and only touches the graph at -5 and comes back up. There's never a time where this graph goes below 0. Okay, so let me do this here. Based upon this graph right here, based upon our knowledge of this, I want to take you on a little bit excursion here. We know this x squared plus 10x plus 20 less than 0 is a no solution. So if you get this part, you should understand the rest of it here. So I'm going to put a little star right here, star, and I'm going to change the problem around just slightly. And if you're getting this, then you got the whole concept here. So instead of being a less than symbol, I'm going to make it less than or equal to. So again, don't need to do all the work because the work is going to be exactly the same. What we're going to do is we're going to find a 0 at -5, and the parabola goes like this. So based upon the inequality, based upon the parabola that we got, tell me what is the answer, and you should be able to tell me what the answer is. Alright, answer should be, let's see, when is this graph below 0? It's never below 0. We figured out that from the last problem. When is it equal to 0? At a single point called -5. So the answer is x is equal to -5. This solution is only true at an individual point, and the individual point is called -5. Alright, let me switch it up just a little bit more. How about if I do this? X squared plus 10x plus 25 is greater than or equal to 0. And again, I want you to think about a little bit more abstractly about this here. So let's think about it graphically here. So if this is the parabola, if I set equal to 0, I'm going to get an answer, and the graph is going to give me an answer of -5. And my parabola is going to be the same here. It goes up, starting from the top, it goes down, touches -5, goes back up. So what's the answer to this parabola? When is this parabola going to be greater than or equal to 0? In this case, all the time, right? Isn't it greater than 0 here? Greater than 0 here? Greater than 0 here? At this point here, it touches 0, but we're including that point. We're including when it's equal to 0 as well. And then it turns around, comes back up. So the answer is all real numbers. Alright, and the fourth type. Let's just see if we got this here. X squared plus 10x plus 25 is greater than 0 only. When is this graph greater than 0? Alright, again, if we set it equal to 0, we get a graph, or we get a point that says that -5 is the answer. Here's my graph. So now the question is this: when is this graph going to be greater than 0? Well, yeah, here, but no, hold on real quick. Not here though. Right at -5, it's not, because we want to know when this graph is greater than 0. It's greater than 0 here, except for that individual point called -5. Then it turns back up again, so that's true the rest of the time through here. So how about this? All real numbers except -5. Okay, those were parabolas. And the reason why we put in test points into them is because that's the normal process, the way we do things here. That's the more like the algorithmic way of doing it. You just sort of process. With parabolas, since we know 7.5, we can sort of know the shape of the graph. With the next two problems here, if you look at this here, we don't know the shape of the graph right here. There's our little problem. So if you don't know the shape of the graph, you're going to have to rely on the test points to make that true. So again, that's why we started off doing it that way in 1 and 2. Problems 1 and 2 of the last of the section, sorry. Alright, so let's go for it here. So we're going to move off the parabola, and we're going to deal with now rational inequalities. We dealt with the rational equations. We had two equals. We had an equal sign here. We can deal with those. That was chapter 5. Now we're going to deal with the inequalities here. So how do we deal with those? Well, the same exact way. We know how to graph or solve an equation, so let's make it into an equation. And let's figure out where our zeros are at. Okay, the only extra little piece right here that you got to think about is, remember this domain issue. If you think about this here, what x would not work right over here? What x would not work? What x would cause a 0 in our denominator? Alright, off to the side here, hopefully you got it right. Something called x cannot equal -1. So let's keep that in mind when we get to our graph. Okay, but what is the common denominator? It's x minus 1. So let's multiply both sides by x minus 1. On the left-hand side, it cancels. X plus 3. On the right-hand side, 0 times that, still 0. So subtract 3 from both sides gets you -3. So here's what we got. We got an answer of -3 for my 0. We also have a domain problem at +1. How do we handle this as we do our graph? Alright, we go off to -1, -2, -3, -4, and at 1, 2, 3, 4. Again, you don't have to put all those numbers in. I just kind of do them here. Gives you extra little room here for my test point at -3. So here's what we do. Instead of putting a closed dot like we did for the parabolas, because this is a domain issue for us, we're going to have to put an open dot. And the open dot means x equals 1 is not part of this inequality at all. It doesn't make sense for this inequality at all. Okay, and -3, we're going to put a closed dot because we're saying, okay, that's when it actually equals a 0. So open dot because of the domain problem, closed dot because that's one of the zeros. Alright, test point, -4, and again, we're going to just test it to see if it's true or false. Alright, hopefully you notice by the end of here, it's not so much the numbers, it's really about the signs. So if I plug in a -4 to that, it gets you -4 plus 3 is a -1. -4 minus 1 is -5, and is -1 over -5, is that greater than, or sorry, is that less than or equal to 0? Yeah, negatives cancel. So technically it's a +1/5, and that is true. Sorry about that. So thinking through here, not thinking correctly here. Let me back that up here. Sorry. -1 over -5, that becomes a +1/5. And the comparison is less than or equal to 0. So 1/5 is not less than or equal to 0. That is a false statement. So I put a little false next to -4. Sorry about that. Okay, now let's see. We've got this part taken care of. We got the part from -3 to 1, and then we have the part that's greater than 1. We've got all these intervals here, so we just took care of that one. Easiest number to plug in the interval between -3 and 1 is 0. That'll be good. Let's test 0 into this. Plug in a 0, makes a 3 on top, a -1 on the bottom, and that will produce a -3, and is -3 less than or equal to 0? Absolutely, it sure is. So true for that one. So again, you know it's true at -1, you know it's true at -2, you know it's true at -2.5, you know it's true at -2.9, you know it's true at -2.99999, but a little different at -3. Okay, one more interval. anything greater than 1. And we're going to test x equals 4, go all the way out here, and that's okay too. 7 over 3, and is that greater than or equal to 0? That's false. Alright, as we look at this here, looks like the true side is over here. Now, negative 3, we are including that because that's when it actually equals the 0, because this little equal to part there. Because this is a open dot, it has to be a parenthesis, because it's saying it's not even part of our domain. And so the only true stuff is right there. And so let's see, how do we write this? Interval notation, negative 3, comma 1. Bracket and parenthesis respectively, or inequality notation, negative 3 is less than or equal to x, which is less than 1. So the number that I want, negative 3 is less than or equal to the number that I want, and the number that I want is less than 1. And number 5, what happens if we are having 2 or 3 rational numbers here that we're comparing? Alright, so let's go for it here. So first things first, let me rewrite the problem here just so I have more space. And then let me make it an equal to as well. Alright, before I do anything else, what can x not be? So going over here, x can't be a negative 1. Because negative 1 plus 1 gives you the 0, and x can't be 4. Right there, we're good there. Okay, now again, we're going to have 2 open dots here then. So now let's go back over here. Common denominator would be x plus 1, x minus 4. Let's multiply every single term by x plus 1, x minus 4. Okay, I'm not going to do it over here because I know that's going to be a 0 anyway, so I multiply here. And again, why do more work than I have to here? X plus 1's cancel, so it's 3 times x minus 4. Careful with this minus sign. X minus 4's cancel, and that's 2 times x plus 1. Again, set equal to 0. Simplifying this, right? So 3x minus 12. How about a minus 2x minus 2? And so eventually, how about we wind up with adding 14 and gives us x equals 14. Alright, the graph. Got to put in a few things here. Okay, negative 1 is an open dot, 4 is an open dot, and we got ourselves a closed dot at 14. And again, this is just to say that it equals, it's part of our domain. The closed dot means part of our domain. And that's when this function equals 0. And then we're going to have to go back to this sign to say, are we included in our final answer or not? Alright, open dots for domain problems, closed dots for zeros. Okay, I'll let you try this here. Go for it. Plug in the test points. Plug in something less than negative 1. Plug in something between negative 1 and 4. Plug in something between 4 and 14. And then plug in something greater than 4. And let's see if we come up with the same exact true and false statements across here. Alright, I'm going to... Again, I did this here already here, so I got a false for something less than negative 1. I got a true for the 0. As you plug in the 0 into the original function, you eventually we get a true statement. Between 4 and 14, I plugged in a 10, and I figured out there was a false statement, and then I plugged in a 20 after 14, and it turned out to be true. So let's see if we can put this together here. So the true interval is right here. The true interval is here. Again, because of the open dots, I have to use parentheses, but I can shade in that area there. Closed dot. Now hold quickly here. Let's go back. Let's go back. Am I including the 14 or not in my original problem? I need to know when this is greater than or greater than 0. It's greater than 0, so no, I'm not including the 14. Because I only want to know when it's bigger than or above the x-axis. Goes on forever this way. And again, interval notation, negative 1, 4, both in parentheses, union for this little extra gap here, and parenthesis at 14 off to infinity. Inequality notation, writing out this side becomes -1 less than x less than 4, or, because that's what this means right here, x is greater than 14. Alright, and that is it. We have just come to the end of chapter 7.